Right. Yeah. So, okay. The other day I had a slight flu, so I had to stop the class. And so, anyway, so we were looking at uh, uh, the option that LSC has not seen anything, and then how do we proceed? And all the physics scale is extremely heavy. So all the physics scale is extremely okay. So if the physics, new physics is heavy, uh, what can one do about it? Meaning, how will you do any physics at all? If the new physics is heavy, you cannot test it at anything. The only hope is that it has remnants leaves remnants in operators uh, which are suppressed. Here, uh, so if the physics is very heavy, you can integrate it out. You can integrate it out, and it leaves a bunch of operators, a series of operators. Okay, it leaves a series of operators beyond. Okay, beyond the simple example of what we have, which is beyond the simple standard model or Lagrangian model. Now, people have known this for a while because they use it regularly in various uh, models, okay, in various cases. So these have been known for a long time, but now because the BSM is also very heavy, you are applying it to beyond physics of standard model. So people have used it for a long time. The ideas of effective field theories, mostly in strong interactions. And especially to understand flavor process. And also in process like positronium, nuclear physics. Um, I don't know of any scale at which effective field theory is not used. Everywhere we are using, including the standard model itself, could be considered. So, what is an effective field theory? The effective field theory is characterized by a energy scale up to which it is always valid. Okay, it should always be characterized by some energy scale. Without that, you cannot. It doesn't make any sense. It's a field theory which is only valid, okay, up to certain scale essentially. There are many kinds of effective field theories. We'll consider ones which are relevant for the standard model BSM physics essentially, but they are used every day in various forms in flavor physics, in collider physics, okay, in various directions, in various forms. Okay, so what is an effective field theory? Effective field theory is a QFT specified by a scale up to which it is valid. Now, it is characterized by two main things: the degrees of freedom relevant up to in that scale. So, within that energy region, okay, so it's not something which can be extrapolated to all energies. So, in the standard model, we did what we did, running of the gauge couplings all the way up to gut scale. Yesterday, we talked about Higgs couplings running all the way up to infinity and everything. Okay, in principle, the effective field theory should not be applied to all scales. It doesn't mean that the theory is valid up to all scales. Okay, it's complete contrast with what we have done so far. Okay, so yesterday I think in the last class we started extrapolating lambdas to very high scales and then said there is metastable vacuum. We started giving all kinds of sand piles and all that kind of business and everything. In an effective field theory, uh, these kind of questions you don't ask. Essentially, you don't say, you only worry about field theories which are valid up to that particular scale. You only ask questions which are relevant up to that energy scale. So within close to that lambda scale essentially. So if you fix the lambda to be very high, all those operators will become irrelevant essentially. They are anyway irrelevant, but they also will become go to zero essentially if you set them to infinity. Now you can, so the two main characteristics which, there are many characteristics of EFT are the degrees of freedom. Relevant at those scales and two, symmetries relevant. What are the symmetries which are relevant at those scales? Now you may not fully appreciate these 2 points. Okay, I'll start giving you simple examples. Okay, I'll start giving you simple examples. Okay, so let's start with QED. Okay, let's start with QED. Everybody knows QED. Okay. So I'll come back to more features of it and everything and general features. So, but just to give you, if I give more a couple of examples, then you'll get the feeling of what I mean to say, what I'm trying to say. So let's start with QED. What are the degrees of freedom of QED? Electron and photon. There are only 2 degrees of freedom. And what is the symmetry? U1. Okay. So LQED is equal to Do you all agree with this? Yeah, I also have to define what is del mu. We have to define the coupling. Let's define the coupling as E, say for example. Okay. Is it valid up to all scales? Does the electron will have other interactions or any other degrees of freedom? Answer. They have weak interactions. So it's obviously not valid at all scales. So QED is not valid at all scales. Let's just say it is valid up to what scale? Any idea up to what scale it's valid? Huh? Yeah, electroweak reality, but yeah, but before that itself you'll start having, yeah, electroweak symmetry scale essentially. Yeah, right. That's right. But what is the scale? Higgs mass. You said something else. Electroweak wave. But wave is associated with something in ZF. Okay, GF. GF. GF is the Fermi coupling constant. Right. Okay. Okay. So now let's say that it's valid up to some scale lambda. Okay. But with only these 2 degrees of freedom. Say for example, let's just say that these are only 2 degrees of freedom. So what else operators can I write? Okay. So I have L effective is equal to LQED plus what is the operators I can write? Right. Psi E bar gamma mu psi E square. Is this okay? You can put PL and everything essentially. Because we are not having, if you put weak interactions, you have to make difference between left-handed and right-handed. If you are not putting weak interactions, let's just say, is this valid? Let's not worry about weak interactions for the present. It's a dimension 6 operator. It's a dimension 6 operator. So it is 4 Fermi operator. Okay, I'll come to the weak interactions, which he has also mentioned. Okay, but what about photon? Yeah. Will there be any other operator only with photons? F mu whole square. Very good. Is this gauge invariant? Huh? This is gauge invariant. Is this gauge invariant? Huh? In fact, this leads to photon-photon scattering. This leads to photon-photon scattering, which is being measured in LHC and other things. Is it the only operators you can write down at this scale, at this dimension? So the first thing we realized is that we can write higher dimensional operators, dimension 6 by lambda square, which are gauge invariant, because I removed the condition that I am sticking to dimension 4 operators. I didn't make anything about weak interactions and everything. I'll come to that in a second. I can write dimension 6 operators. Just that I removed the condition that at the renormability condition, essentially, that lambda square. I have two operators, but are there any, if I stick to dimension 6, are there any other operators I can write down? X mean infinity tilde. Is it correct? Is it gauge invariant? So, what are the things which will appear here? Are these coefficients known? What are the coefficients known? In full QED, I can calculate essentially. In principle, I can calculate essentially. As of now, I don't know what those coefficients are. So these coefficients, I call them as Wilson coefficients. These are coefficients which I call them Wilson coefficients. So I'll put C1, C2, C3. Are there any other operators I can write down? Can I write sigma minu operators? Is there any dimension 5 operator I can write down? Huh? Why are you saying no? Why are you saying no? Actually, yes. He has. Right, right. Very good. Excellent. It's a very important operator. Okay. We didn't write down that particular operator essentially. That's a very important operator at dimension 5. So we started directly writing dimension 6 operators. Okay. But a non-trivial operator which comes essentially is generated in QED at dimension 5. So it has only one power. Is there anything else possible at dimension 5? This operator is extremely important. You can also put a gamma 5. In fact, this leads to what is called what? Yes, dipole moment. Okay, magnetic dipole moment. So what about, so this, you can imagine that it is a spin flip with gamma. If you write a Feynman diagram associated with it. In QED, in full QED, it gets generated by the Feynman diagram. So here we just put it with a blob because it's an effective vertex essentially. So similar, the same diagram also gives this one. So here you have gamma, 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 electron, electron, electron. So this one, this is photon, photon, photon. So it's photon scattering with itself. What is this scattering called? He is Bohr's student. After doing this calculation, he left physics and became biology. Okay. Okay. Delbruck scattering. Okay. Delbruck scattering. He did it with QED. With the box. So we had to have, so all this looks nice. So we had to have an organizing principle. We had to have an organizing principle. So in general, an effective field theory is valid up to that scale. So we say that, okay, let me put higher order terms also, okay, suppressed by that scale. Higher order terms also which are suppressed by that scale. Essentially, they can play a role essentially. They have to be the same lambda, but there is a caveat. There is a caveat because some lambdas can, we'll see. Here they have to be the same lambdas because they all correspond to one symmetry. If you have complicated symmetries, like for example, baryon number, lepton number also, and so on. So there could be some symmetries, extra symmetries, which can remove some of the terms, essentially, which can remove some of the terms. In general, like I said, that is the reason why you have to know what are the degrees of freedom and what is the symmetry. There is no other symmetry here other than U1. Okay, there is no other symmetry other than U1. F mu has only one name field. Del mu A. It's an effective vertex. So you can imagine that some other particle, heavy particle is there. Okay. And so this heavy particle could be a boson, should be a boson in principle, just from Lorentz statistics. Okay. Lorentz invariance, it should be a boson. So in the standard model, this will be W boson. So if it's a vertex, effective vertex, so you normally, so, okay, so you normally write ordinary vertex as IE gamma mu. Okay, an effective vertex like this case essentially, because it also changes the chirality. Okay, if you put the chiral signs, it should be like this. Okay, it will be I sum C by lambda sigma mu. You can write it in terms of the momenta. It will turn out to be the difference of the momenta P1 minus. So in your QED, you must have studied Gordon identity. So you can write it in terms of the Gordon identity, and the Gordon identity will give you in terms of the gammas of the P1 minus P2. But since we are in effective field theory, we don't care about what is the full, how this diagram is being generated. It only tells you that there is a new vertex which goes with sigma mu nu in QED. Okay, in QED there is only one vertex, but in an effective field theory you have a new vertex. Okay, you have which has a new vertex which the by definition, which goes by sigma mu nu. By that means that it will always, because of the photon, it will always flip the chirality of the thing. Sigma mu nu is gamma nu, and it will always flip the chirality of the electron. So this vertex itself flips the chirality. Okay, whereas QED vertex does not flip the chirality. Here left electron becomes right electron, whereas here it doesn't care about the chirality. Electron remains, chirality is not changed. Okay. Similarly, you have an extra vertex like this, 4 Fermi vertex. Okay, and you can work with this thing completely. You can work with this. Try to renormalize it. In some theories, you can renormalize it at one loop. Okay, it is a valid full quantum field theory, which can also be renormalized with dimensional regularization up to certain levels. Not all orders. You don't have to do all orders or something essentially. Now let's stick with the QED example and say if you have weak interactions, okay, QED is valid up to a certain scale. Now here we just said it's valid up to certain scale lambda. We didn't identify what the scale is. We didn't identify what the scale is. So we can identify what that scale is and can also estimate what these coefficients are, because there is a full theory about QED. Okay, there is a full theory about QED. So you can derive step by step QED from standard model. Okay, and match these coefficients with the calculations in standard model. So that is called matching. If you know the full UV theory, so here I don't know what is the UV theory, but I will assume that it is valid. It cannot be valid up to all scales. It can be valid up to certain scale essentially. Okay, so if I know it's valid, we'll do some matching actually. Some simpler matching will start and everything. But before that, I want to continue with the QED example. I'll just give you one particular example with flavor violating terms. I mean, not flavor violating. What do you call chirality violating terms? So if you have standard model also, then you'll have terms like you should put PL and PL and okay. So this is a term coming from Fermi theory. This is purely a term coming from Fermi theory for neutron electron scattering. Now I introduce one degree of freedom, which is a neutron, okay, which can exist below the electron scale. QED itself is purely has only 2 degrees of freedom, electron and photon. Now I introduce a new symmetry. I don't say symmetry, but a new theory, which is Fermi theory. The moment I introduce Fermi theory, there can be, I am still sitting at the electron scale only. I am not going beyond the electron scale. But below the electron scale, there is a new degree of freedom, which is the neutrino. So I had to write this term. So if I extend the symmetries, or automatically a new degree of freedom comes into the picture. Automatically a new degree of freedom. Electron will not interact with the with itself. Okay, in weak interactions, it interacts with corresponding neutrino. Okay, so this is your neutrino electron scattering. which is a 4 Fermi index, which has GF by root 2 as the vertex. So what is the vertex here? IGF by root 2. Now what is the mass dimension of GF? -2. So if I put GF, it's automatically valid. If I put GF, it is automatically valid. So QED has all this effective Lagrangian. In fact, this particular Lagrangian is called Euler-Heisenberg Lagrangian. This is used in string theory and many places actually. So also in studying many places in condensed matter. This Euler is not the same other Euler. Okay. Okay. So okay, I'll give you one example, a very nice example, which I like very much. Photon decay into neutron. No, which one? This is just electron neutrino scattering. This one. No, this will just be the. No, this will be just a correction to the neutrino mass. Nothing else. Want to put a photon? You can put, yeah. But a particle cannot decay into itself. Okay, it has to be some other particle because the masses are same. Okay, it has to be. So suppose if you have mu which is heavier and nu e which is lighter, you can think of some weird class of diagrams which can lead to something. Neutrino decay is non-zero, meaning it can be there. I'm saying. What? No, this is not the diagram for neutron decay. Okay, okay, right. What is that theorem called? You should know this theorem. Odd number of external photons, it should go to 0, but not in decays. Scattering. Okay. You can have a decay, say for example, b to x gamma. That's possible. Yeah. Anyway, now that he raised that a diagram should not have odd number of external photons. Next time I'll bring some chocolates. Who answers the question? Okay, I'll give that chocolate to them. Okay. So you tell me next time what is the name of the theorem you mentioned actually. Okay. Yeah. No, it's not Froesa theorem. No. You said Froesa? Froesa's theorem? No. It's not Froesa's theorem. Froesa's theorem is bonding on amplitudes. Yeah. So let's do a simple example. Let's do this is one of the simplest examples. Now that we are all in the BSM class, we know that we should get neutrinos a mass. So how will you get neutrinos a mass? Okay. So the simplest way having neutrinos mass, okay, is by adding right-handed neutrinos into the theory. Okay, so I add a coupling y nu L nu by tilde, which is nothing but Higgs, plus, if this is a right hand, you need to know, right hand you need to know can also have something called a Marana mass. How many of you are familiar with Marana mass? You all, okay, good. So it can also have a Marana mass. 1 by. So, but you have to worry about the HC and everything. If it is a generic, um, if it is uh, a general, what do you call, matrix, essentially, if you want to make it in 3 dimensions. So, let me expand this L, well, here, and H tilde. So, this entire thing just becomes Y nu, okay, nu L bar nu R. Put the web, V plus H 0, and I'll work in unitary gauge. Okay. So these are the only two terms. Now, if I write this in the Marana mass basis, I don't have to write this as nu r c nu r. I can write it in terms of nu r nu r. Okay, I can just write it as half nu r nu r. Now there is a term proportional here, which is mr, and here there is a web. Okay, y times web. I'll call it as md. Okay, which is associated with Dirac masses. Okay, md is equal to y nu times v. Mr is this term. Okay, so mr. There is a double counting here. If you write in terms of Weyl fermions and put a hc, okay, so you can put a, you need to put a half so that the equation of motion. Now what you can do is you consider the limit mr is much larger than md. Okay, now this is very high mass compared to md. Now if I want to write an effective theory, of only nu L or of any standard model or something, essentially, which contain valid much below the scale of mr or up to the scale of mr but not beyond it. Up to the scale of mr I want a valid. Then I should remove all the degrees of freedom associated with that scale. All the degrees of freedom associated with that scale. How do I remove the degrees of freedom associated with the scale? I integrate them out. Integrate them out, in other words, is differentiating them out. Okay. So what I do, I just do this is some Lagrangian which I call LS, and this gives me md nu L plus half mr nu R. So integrated out means I take the equation of motion and set it to 0. Okay, set it to 0. The equation of motion should go to 0. Now I can solve for nu R, the heavy field. I can solve for the heavy field. So because I want to remove the degrees of freedom, okay. So the heavy field degrees of freedom has to be replaced in terms of the light field's degrees of freedom. So nu r becomes minus md by mr, okay. Forget about the factor 2 in the equation of motion, goes away, times nu. So this term by definition will go away by putting this back into this. So what will happen to this term? This term will become L effective is equal to minus md square by mr. Your there is also hc essentially. So this is your first effective field theory you have done. Simple integrating out the right-handed neutron essentially, which can be explained. So you are only valid up to a scale below mr. The theory is valid. Now let's write down the entire thing in terms of effective field theories. So in terms of effective field theories, how do I write this operator? I don't know. First, did you follow this? Did you follow this? You just integrated out or differentiated nu r and wrote the heavy degrees of freedom in terms of the light degrees of freedom. Substituted it back into the original Lagrangian. Okay, substituted it back into the original Lagrangian. This will just vanish. There will be a small correction essentially. Okay. Where? No, you put it back into this. This will be highly suppressed essentially. This will be next order term, md power 4 something. Next order term in effective. So you can put it back. So it will be suppressed by mr square. Md, it will be the same term actually. Sorry, it will be the same term. Yeah, it will be the same term. You'll end up having md square by mr. It will be the same. So there won't be any more heavy degrees of freedom in your Lagrange. Okay, any heavy degrees of freedom in your Lagrange. So keep this as it is. Okay, let me call this as equation 1. Just classical equation. This is tree-level integration now. Yeah, this is on tree-level matching. This is enough, sufficient for most of the purposes. So this is tree-level matching. You can worry about one loop matching and light heavy degrees of freedom, then it's super complicated. Okay. Because we are all at tree level, no? Every term is tree level, so we can get away with tree level matching. So keep this as it is. Now come back here. What are the symmetries here? SU2 cross G1. Okay, SU2 cross G1. It's a standard model symmetries. So all the particles of standard model are there. But what is the symmetry associated with nu r? Singlet. It's a singlet under all possible symmetries essentially. Okay, so you get this particular thing essentially. So you are adding a heavy field with no implications for the symmetry, and you are integrating it out. Now let's stick. So that means that if I stick to the same symmetry, I should be able to generate this term if I write an effective field theory of the standard model. Right? Sticking to the same symmetry, I should be able to generate this term in the standard model. And what should be the dimension of this term? It is suppressed by 1 mass power, so it should be dimension 5. Should be dimension 5. So let's write down the standard model. So the degrees of freedom of the standard model are L, H, E, nu, and there is no nu, sorry. Okay, Q, U, D. That's it. Now we are not worried about anything in the color sector for the present. We'll forget about that. So what would be? So I have the standard model. Now, assuming the symmetry of the standard model, what is the first term I will write down? I can write down at dimension 5. Okay, LH square. Now, is this term same as this term? With the wave. The moment H becomes wave, so this should give me, okay, nu square. So this term is same as so. So the C by lambda can be matched okay. This is the first tree level matching we have seen essentially. So C by lambda can be matched with MD square by MR. Okay, so this is one example where the seesaw mechanism appears as an effective field theory. An effective field theory, and the first term in the expansion of the standard model at dimension 5 is the neutrino mass term. And it turns out this is the only term allowed at dimension. Okay, it is the only term okay. Example 3. So these are easy examples. Okay, all right. Yeah. Now you all heard about K0 K0 bar. Okay, K0 K0 bar. Okay, we'll consider an example um, in QCD. Okay. So K0 K0 bar has plus the switch diagram. Now, what is the mass of the K0? Now, what are these particles? These are W bosons. And what are these? Up-type quark, charm quark, top quark. Okay. Same thing, up-type, top, charm. Now, these are super heavy. W bosons are heavy. What is the mass of K0? How many MeV? It will be MEV, GeV, any scale, TeV, whatever. Huh? MEV. What is the mass of S quark, say for example? Huh? Somebody is checking. K0, what is the mass of K0? 400 MeV, something like that. Just check how much it is. Okay, 497. K0 bar. So I was in the right ballpark. K0 bar. So what is rig point is delta MK. In fact, it doesn't matter. So let's just take it to be K0 we need, that's all we need, the average mass. What is important is this mass difference. The mass difference by the average mass of the K0 bar is around 10 power minus 5. And this sets the oscillation. How K0 goes to K0 bar essentially. This sets the oscillation. Now you see this is extremely tiny mass. Okay. This sets the oscillations and this really puts very strong constraints. Now we are sitting at half a GeV. At that scale, if you believe in effective field theory approach, you only have to consider only those operators which are relevant at that energy scales, with only those fields. So those fields which are relevant at those energies, essentially at the masses of around the mass of Mk, essentially you cannot consider C, T, Ws, none of them you can consider. All of them are integrated out, should be integrated out. So the only thing you can consider is D and S and D bar and S bar. Okay, because K0 is made up of D and S, okay, D bar and S bar. So the first step is write down all possible operators, Up quark will be there, but it can be integrated because it doesn't come alone. It always comes with W. This is an example of light heavy mixing. Pardon? So you don't know about high energy theory. What you are worried about is that there is a meson made up of two quarks. I know the meson, how it is mapped into these two quarks. Okay, and these mesons are somehow interacting with other converting into d bar s bar. S bar d bar bond state is getting converted into s bar d bar s bar. And what are all the possible operators I can write? What are all the possible? Okay. And now what will be these operators? What is the dimension of these operators? This will be 4 Fermi operator. You are not convinced. So you are not starting with K meson bound state. You are first working in the quark level, then mapping it with the K meson, because the process is happening. Okay, this bond state is something called a long distance effect. This is a short distance effect. Okay, this is at a much higher momentum. Okay, because weak interaction scale is what? 200 GeV, whereas the formation of the bond state is 1 by lambda QCD. Okay, so this is the bond state formation. It has a lower state, much lower energy scale, whereas this is a short distance effect. So this is a long distance effect. So you decompose both the things. You factorize. Okay, first you calculate all possible interactions which you can write down at the quark level, essentially, assuming that this entire thing is integrated out. Okay.
The mass of the kilo.
Mm.
Then can we still talk about interaction between individual quarks?
Because it is bound state of two individual quarks.
Yes, but then can we, like, will the physics?
No. Yeah, the physics is caused by the quark converting each other.
Yes.
It's a short distance effect. K0 getting converted into K0 bar is because inside the physics is a short distance effect. The bond state is just a QCD thing. This is a weak, another way is this is weak interaction scale, that is a strong interaction scale. The interactions are completely different. Now, is this difficult or is it okay? Okay. Okay. Now what you do is also called as operator product expansion. You see this all the time essentially. So you write down, you say that I don't know what is the CK matrix, I don't know how to calculate all that stuff essentially. I'll write down all possible operators. In principle, you should only write down, because it's a weak interaction process, it should be only chiral operators. So DL goes to, only DL goes to W, right? Essentially, right? This should be, so what you should write down is essentially DL bar SL. So this is a scalar operator. Okay, this is scalar operator. So you put some Wilson coefficient on the top. Then you put another operator with a vector. Okay, so and so you can write down all possible operators with all the bilinear covariants. Then you can also say pseudoscalar. If you write DL and SL, you don't put a gamma phi, of course. Okay, but in principle, if you write down the basis in terms of just D and S, you can put a gamma phi. You don't have to put a gamma phi. All the bilinear covariants you can write down. Then you can also have now what you have done is there are up to 9 operators essentially. what you write is this basis of all possible operators, which is called Wilson expansion or operational product expansion. Now, all of them will not contribute to every process. Okay, some of them will contribute to some process. Say, for example, then what you can do, K0, K0 bar, then there could be other operators essentially. So, other process K go into some K pi, 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 or K go into 2 pi, K go into eta, or K go into all those processes. You have one particular operator product expansion. And use that to explain all possible phenomena in strong interaction. Now, what are the relevant degrees here? Only the D field and S field. And what are the symmetries here? No, you are missing one more. These are colored. SU3. So there is SU3, and is there SU2 here? No, SU2 is broken. Okay, SU3 QCD times U1 QD. With these two, you write down all possible operators. And given a process, there could be operator mixing. That means in some process, there could be two operators which are acting essentially, which are contributing. And there could be mixing between these operators. Okay, and there could be sometimes instead of F mini, you can also have chromomagnetic operator also, because the gluon also can play a role. Just like F mini, you can also write down an operator with gluon. So that will be a chromomagnetic operator. Okay, so depending upon the process, so you use this particular effective field theory. And what is the dimension of each of them? Dimension 6 operators. Okay, and they are all suppressed by, and 1 by lambda square in this case, because we know it is coming from weak interactions, this will be just be equivalent to gf square by root 2. Why this has become such a powerful tool is because you can explain everything in this particular basis, all the possible. So there will be up to C9 operators, C1, C2. So you, when people in B physics community or K physics community, the same thing you can do with B physics also, but there it's a little bit more complicated and everything. They'll keep saying that C7 is contributing significantly, C3 is contributing. Two operators if I talk, so they talk like chess people. Okay, okay, C7, C2, something like that. Okay, now given this operator should be mapped into the bound state. Into the bound state, right? Essentially, so that comes with a form factor. Essentially, that comes with a form factor, Fk or something. So you take this operator, merge it with K0, say C1, take a process K0 bar and calculate it, and then this will be some Fk square, some function will be there. Now Fk square, you have to know what it is. You get it from lattice most of the time, or chiral PT. Chiral PT is less, okay, but it is essentially learned from chiral PT, which is another effective field theory. Or nowadays most of them get it from lattice. So each operator map into this particular thing, and if you go and check in the library of chiral PT, it gives you what is this operator is equivalent to. You put it there and you get this measurement from. either chiral or you go to lattice and check what this number is. Many of the chiral PT constants are also fixed on lattice. So it is a combination of chiral PT plus lattice people can use. Okay. Now this is a very powerful tool. Now you keep hearing that there are these anomalies in K physics, there are these anomalies um, in B physics and so on. So, okay, how will you deal with them? So that means when there are anomalies, what it means that this present set of operators are not sufficient to explain the data. So the present set of operators are not sufficient to explain the data. So you imagine a new set of operators, okay, which are not GF by root 2, which don't have this mapping, but some operators C1 tilde by lambda square, C2 tilde by lambda square, but which have the same Lorentz structure. They have the same Lorentz structure. And now you play with those operators, and now you can also make them right-handed because it's new physics. You don't have to worry about chirality. You can put right-handed currents and so on. So, okay, and then see adding this new set of operators, putting it back into these relations, check if it satisfies the data. That is the entire game of V physics. So every time, invariably, the experiments give you anomalies. Then you play with this game. If you know how to do this game, you are done. Okay. So now there are more complications. While I said this is easiest, but if you want to do it accurately, it's much more complicated in the sense that you have to do one loop matching. There are strong interaction corrections. There are, so suppose if the process is also complicated, say for example, we are considering something like a hadron going into two hadrons. This process is dominant. So for example, B2, okay, phi short. This process is super complicated because all of them are hadrons. I mean, they're all okay. They're all mesons. Okay, they're all mesons. So you need to use factorization theorems for it. How will you start the process essentially? Because how is this? It's a completely strongly interacting process. So there could be millions of gluons going around and everything. So you have to somehow stop the gluon somewhere. So this gluon should not talk to this gluon, otherwise you cannot identify it as K. This gluon should not talk to this gluon. So you have to stop somewhere. So you say that all the gluons associated with Ks are factorized into this particular case. You can factorize the scales essentially, and there are some QCD factorization theorems which help you to do with this. Okay, so yeah, that is complicated, and this entire business of new physics appears in this particular case. Okay, so what we have seen today are three examples where within close to standard model essentially, that you have in every case we showed that if you know the degrees of freedom. So yeah, the question is, why did, even for new physics, I didn't change the degrees of freedom. In effective field theory, that's the main important point. I just wanted to that's the point I want. You're not changing the degrees of freedom. You're not introducing new degrees of freedom below that scale. There are no new degrees of freedom below that scale. Okay, you are dealing with only the existing degrees of freedom, but you are only introducing new operators. Symmetry is also, we are keeping the same symmetry. Yeah, dr doesn't violate, because you remember that this doesn't have a C2L cross symmetry. This is weak scale. W is integrated, everything is integrated. So below that scale, there is no SU2L cross U1 symmetry. There is only SU3 QCD and U1 QED. This written in the broken phase. Only when we are writing the standard model operators, we have to worry about DL and SL. Okay, we are far below the scale of W. So if we go beyond that, the symmetry is valid. Much below that scale, symmetry is already broken. Okay, so if you are looking at SMEFT, we'll see. I'll systemize this. Okay, I'll introduce systematically, but here today I'm giving you examples essentially. Okay, so if you are dealing with SMEFT, okay, then you have to worry about the symmetry being SU2L. How do you introduce right-handed currents? In SMEFT, you cannot introduce right-handed current unless you enlarge the symmetry. Okay, I'll tell you. This is called VWEFT or LEFT. Okay, in this case, you don't care about any other symmetry other than these two symmetries, and no degrees of freedom, no new degrees of freedom, but you can write down all possible operators. Okay, so you have dr bar, sr bar. No, W is integrated out because we are sitting at a scale very close to the mass of the kaon. W is 200 times or 300 times heavier than the mass of the kaon. Already broken. We are not. So unless you are sitting at a scale very close to, say, W mass or beyond the W mass, say for example, say about a TeV or so, you don't have to write everything in terms of SMEFT. So today my aim was to give you these three examples essentially. Yeah. Now there are. This is very nice. There I didn't mention something called operator product mixing. Then there could be an anomalous dimension max, because when you actually do the calculation, what you do is you write the operators. So if you want to do a standard model prediction, okay, you write these operators just below the electroweak scale. From electroweak scale, you have to run them down all the way up to K1 mass scale. So these operators will mix. So you have to write corresponding RG equations for them. Okay, the RG equations from the electroweak scale down the way down to here, if you want to do the standard model matching correctly. And then you have to do the matching at the electroweak scale with the standard model Lagrangian, and at the weak scale with the K1 parameters. So you have to do the matching, and then after taking the running effects. So if you start with running effects, so what happens is initially the operators mix. What happens is due to the RG running, the renormalization group running, the operator, so one operator will not remain one operator at one scale. So if one operator is contributing at one scale, it could be two other operators at a different scale. Like what you are saying, if I map this one, this will become another operator. That's precisely what happens. Essentially, you can have a combination of two operators which will behave like another operator, which will also could contribute to the process. Okay, so all these people, when they say one operator at a time, two operators at a time, they are not really valid under RG analysis. But luckily, this RG analysis is most of the time very small effect. But if you want to be very accurate, you have to take it into consideration. In some cases, it's not so small, especially the strong interaction scales, essentially. Okay. When you do that, and Manohar and company got the prize essentially. I don't know, it was shared essentially. They derived the RG equations recently, systematically. These RG equations were known right from the 80s, but they were known not systematically. They were known for certain parameters. Everybody derived their own RG equations for whatever was relevant. For example, Buras has derived them and so on and so on. But systematically for LEFT, they have derived it. For SMEFT, they have derived it. Complete detailedly, they have derived all the RG equations starting from SMEFT to LEFT to so on. So I'll tell you all the distinctions later on in the next class or something. So when you do these RG equations, there will be operating mixing, and then at the weak scale, you have to low energy scale, you have to map it to the corresponding form factors and the processes. Okay. So all this analysis which people do is at one operator at a time is not really valid unless you have very strong reasons to show that only one operator is dominant for a given process. Okay. Yeah. So I'll stop here. So to summarize, I gave you three examples. One was with the seesaw mechanism. One was with the QCD. Another one I don't remember what was the QED. Okay. So in the next class we'll systematically see the characteristics of effective field theories. What is okay, and then classify all effective field theories. Some of them relevant to SMEFT. So we cannot classify all possible things. There is something called SCET. There is something called so many. Everything is an effective field theory. Okay. Yeah. Um, and what are the interesting problems people are working on these days? That's the basic idea. I want you to give in a picture of it. There are a lot of things one can do. Okay, even though it looks like there is nothing one can do, because phenomenologically it's not as exciting as discovering a particle, because there's no particle. You're only dealing with standard model particles. But you can do a lot of theoretical examples, and you can put strong constraints theoretically on what kind of extensions which can satisfy the standard model, beyond standard model. Okay, I'll stop here essentially. Yeah.